And yeah, it's acid catalyzed reaction, and we are getting this particular methanol and that particular carboxylic acid here, right? So this particular bulkiness impact on the rate of hydrolysis here. That means upon substitution of your bulky groups in the drug compound, it leads to decrease in the rate of reaction here. Ultimately, it is impact, or it is decreasing your biological activity. Okay, so see that you when you are trying to introduce a substituent here, so you means better to introduce a small groups here. Okay. Okay, so here the size of R affects the rate of reaction by blocking nucleophilic attack by water. Okay, so you see generally here this hydrolysis reaction. Okay, hydrolysis of ester. It is a nucleophilic substitution, right? Here the from this water OH minus this basis, so it is going to attack at your particular, right? This particular ester carbonyl group here. Then expulsion of your methoxide group is takes place, and finally this part is okay, converted as a methyl alcohol, and this part is converted as a carboxylic acid, right? So when the size of your R group is increases, then it prevents, okay, it prevents to approach this nucleophile. Okay, because because the size of this R group is large, so the OH minus, it cannot be attacked at electrophilic carbonyl center, because where it is expelling that particular, right? It is not facilitated to the attack at the electrophilic center due to this bulkiness. So the OH minus or the base, it won't approach this particular carbonyl center. That's why the where the small groups are preferable in the drug structure while we are doing that drug modifications. And you can calculate the ES value, that is a steric constant value here by this formula. So where the ES equal to log K, and where this is particular your R COCHC, this is your compound, the ester compound with a variety of substance, minus log K CH3 COCH3, means it is a methyl methanoate, it is a standard one, the standard ester compound. And with reference to this standard methyl methanoate, where this particular R group upon substituent of the different alkyl groups in this particular ester, so you can see the changing of the values of your ES here. Okay, and you can okay, so this particular table ES values for the various substituent here, right? So this particular table, it guides us to which group we need to consider for the generation of the PSR model here, right? Or which group or the which right alkyl groups are the group is required to uh, get the better value, better biological activity value, uh, right? So it is giving some idea about that, right? The substance which group we need to consider for this to increase the biological activity. And where they are taking this particular hydrogen as the standard one here, where its value is 0, and then methyl. Okay, so methyl, it is value is 1.24 here, minus 1.24, and propyl group minus 1.60 here, and tertiary butyl group minus 2.78 here, and fluorine with minus 0.46, and chlorine is 0.97 here. So like that, here the and amine group is 0.61, cyanide nitrile group is 0.51 here. So these are the values given for each and every substituent, right? Okay, so each and every substituent here. So depending on our requirement, depending on the value, right, the we need. So you have to select that substituent, other you have to select that particular group in order to increase the biological activity here, right? So you try with the different substituent here and see that in which group is increasing the value. Then you consider that group for the generation of the QSR equation here. Okay. Next, Hans analysis. So Hans analysis. So this is also one of the right one of the method to calculate the biological activity by considering the various physicochemical parameters here. Okay, so in the previous cases where we are taken only one, okay, only one physicochemical parameter here. But in the Hans analysis, so we are considering all the physicochemical parameters. Okay, so we are deriving the equation by taking all the parameters here, like okay, so steric factor here, okay, steric constant and substituent constant and lipophilicity constant are the partition coefficient. So all the parameters are, all the physicochemical parameters are the descriptors are considered to generate the equation here, right? So that is the advantage of Hans analysis. Generally, we call this is the multi-regression. Hans, okay, Hans multi-regression analysis. So multi-regression means we are considering all the parameters in one equation, right? So in the previous case, you can see, for example, here the top two steric factor. So we are seeing only the steric factor. We are considering only the steric factor to generate the QSR equation. And in the Hans Fujita, okay, Hans Fujita substituent constant, that is a pi. Okay, so pi is a Hans Fujita substituent constant here. So we are we are considering only the substituent constant here, substituent. And here is we are considering this particular steric constant. And in the partition coefficient, we are considering the log p value. Okay, so in all these equations, in all these okay cases, so we are considering only one factor. We are okay, so we are considering only one factor here. But in this Hans multi-regression analysis, so we are considering the all the factors. Okay, so we are taking up all the factors, all the descriptors, all the physicochemical parameters in one equation here, right? So then, so it will give the more prompt values here, more reliable values, and more precise values to for this okay to generate the PSR equation or the model here. Okay. And when they are considering this, when they are generating this Hans model here, so actually okay, so they are okay, so they are explained by the two factors like pharmacokinetics and pharmacodynamics here, right? So they are considering these 2 points here by keeping right. So keeping these 2 points in their mind, so they are generated the Hans multi-regression analysis. And you know that where the pharmacokinetics, which explains your the journey of the drug. Okay, pharmacokinetics explains the journey of the drug. Journey of the drug means where the means how efficiently the drug is absorbed and how efficiently the drug is distributed through your body tissues here. Okay, so that is explained. The journey of drug is explained by your particular pharmacokinetics here. And pharmacodynamics. So the pharmacodynamics explains the binding of, okay, the efficiency of the drug, right? The efficiency with of the drug to bind with your receptor active site here, right? So how efficiently the drug is binding with your receptor active site. So that thing will be explained by your pharmacodynamics here. Okay, so these two points. So in the drug chemistry or in the medicinal chemistry, so the medicinal chemistry is works on these two principles here. Works on these two principles, like pharmacokinetic studies here and pharmacodynamic studies. And pharmacokinetic studies explains the ADME properties generally, right? So it explains the ADME properties. ADME nothing but your absorption, distribution, metabolism, excretion here. So how efficiently the drug is absorbed with your body tissues, right? And how it is going to distribute it through your body tissues here. And then after showing its activity at that site of action here, so then it must be converted into the metabolite here, secondary metabolite, and finally you need to excrete through your renal system. Okay, once the drug is showing its action at site disease center, okay, or the disease site, so the drug must be eliminated or the excreted through your renal system here. Okay, so these are the ADME properties which is explained by your pharmacokinetic studies here. Then the pharmacodynamic studies which explains the binding here. So how efficiently bind your drug with your receptor active site here. Okay, so generally the efficiency of the drug, the binding efficiency of drug provides some more activity, uh, right? So the drug activity here. And you know that the binding is in various means, like so it is the drug will be binds with the receptor active site by through hydrogen bonding or through ionic bonding here, hydrophobic interactions here, van der Waal interactions. So these are the interactions which can be observed, uh, the drug receptor interaction here. Okay, so this particular binding interactions will be explained by the pharmacodynamic studies here. So when they are considering all these when they are proposing this multi-regression analysis, the hands, okay, so they are considering all these 2 points here, pharmacokinetic studies and pharmacodynamic studies. So based on these principles, they are proposed a multi-regression analysis, and which is incorporated all the parameters, like you can see the equation here, the log 1 by c, log 1 by c nothing but the biological activity here, equal to k1, right? Here the k1, it is a constant, k1, k2, k3, these are the constant values here, k1, k2, k3, k4, these are the constant values here. K1, the partition parameter, right? K1 into partition coefficient. Partition coefficient nothing but it is a ratio. Okay, so partition coefficient nothing but it is a ratio between the solubility, right? The solubility of your drug in the N-octanol by the solubility of the drug in the water. That is a partition coefficient here, right? So K1 into partition coefficient plus K2 into electronic parameter, right? K2 into electronic parameter here, plus K3 into steric parameter, plus K4 here, right? So that is log 1 by c equal to K1 log P plus K2 sigma plus K3 ES, top to steric factor, right? This is the equation. Okay, this is the Hans multi-regression equation, which is showing the, okay, which is means showing the relationship between the log 1 by c, nothing but your biological activity, with all the parameters like partition coefficient, steric factor, electronic factors, substrate constants here. And they are succeed in this particular proposing of this Hans analysis, multi-regression analysis, and some right disadvantage also there with this particular Hans analysis here. And you can see the disadvantage of this Hans analysis. Yes. So here the one of the major disadvantages in the enhanced analysis is the stereo chemical consideration, such as potency differences between the optical and geometrical isomerism, is not taken into consideration here. Okay, so generally in the drug chemistry, the stereo chemistry plays a very important role, right? So as we discussed in the chiral drugs here, right? So already we discussed the importance of the stereochemistry in the drug chemistry in the chiral drugs here. Okay, so like you know that eutomer and distomer. So what is a eutomer generally? Where the highly active compound is a eutomer, and distomer is a low active compound, or the inactive compound is a distomer here. Okay, so only due to the spatial arrangement of the group, only the difference in the arrangement of that group group is attributes more activity and inactivity here, or the less activity here. So here this QSR model, QSR studies also uh, useful, or it is proposed to invent a drug. Okay, so this particular QSR model is, as a QSR chemistry is, it is useful in the drug chemistry actually. So, and it is used in the drug designing, CAD technology, computer aided drug designing actually. Right. So while we are doing this QSR method, we are approaching this QSR method here. So we need to consider the stereochemistry as a major factor here, right? But this Hans analysis, okay, Hans analysis, when they are proposing the Hans equation, the Hans multi-regression equation here, so they ignored with the stereochemical factor here. That is one of the major disadvantages of your Hans analysis here, right? So they are not taken consideration of the stereochemical factors here. And where the conformation changes at the receptor is ignored. Okay. So actually here, the conformation of the compound also considered, right? So because the conformation of the structure or the conformation of the compound also plays the important in the uh, biological activity actually, right? Because you see conformation nothing but where the cystons, okay, or the means orientation of the groups in the axial direction and the equatorial direction. So that is a conformation. Okay, so endo, exo. So these are the conformations of the structure here, the other compound. So having that groups in the axial direction or the in the equatorial direction also brings some changes in the activity, biological activity. So the Hans analysis, they are ignored, they are omitted this particular uh, conformation changes, and they are omitted these particular stereochemical factors. Okay, so this is also one of the disadvantages of this Hans analysis. And metabolism does not interfere here. So as per the Hans multi-regression analysis, as per this Hans idea, they are not considered the metabolism here. Means metabolism does not interfere in the this particular studies here. Okay, so actually here the metabolism also plays a role in this particular drug means biological activity. Okay, because for example, if that particular drug compound after showing the action at disease site here, so it need to convert into the non-drug compound like secondary metabolite here. So if it is not converting into metabolite, okay, the pharmacological activity or the its activity will still persist. Okay, the activity still persist here. So it may impact on the biological activity, right? So here the drug compound must be converted into the non-drug compound like metabolite here. Right. So that is a procedure in this drug chemistry, and we will we'll choose those drugs which are easily metabolized after showing its activity here. Okay. So while they are proposing this Hans analysis, Hans equation, generating the Hans equation, so they ignored with this metabolism factor. Means they thought that the metabolism is not a important factor, and it is not interfere in this particular biological activity, right? So in the actual idea where the metabolism also plays an important role in your biological activity, right? So this is also one of the mistake of your Hans analysis. And linear free energy terms relevant to the receptor affinity or additive, means where the linear free energy terms, you know that linear free energy equations, this is also one of the top equation, right? So top derive the equation for this linear free energy. Already you have come across in your physical chemistry topic actually. So this is also additional property, additional value, right? They propose it's this is also one of the mistake generally. And polarity lipophilicity relationship is linear or parabolic. Okay, so here the polarity and the lipophilicity. Generally here the polarity and the lipophilicity relationship is linear or parabolic. Means they are not propose which what relation means the relation for this polarity and the lipophilicity. So in general, the polarity, right? So when the polarity is increases, the lipophilicity is decreases actually, right? So it is inversely proportional. So lipophilicity means where the non-polar compound, right? Because of the lipids, generally the lipids are the organic compounds generally. So the non-polar compound are highly soluble in the lipids, and the polar compounds are less soluble in the lipids and more soluble in the water generally, right? So highly polar compounds are water soluble, less polar compounds are lipid soluble here. Okay, so here this polarity and lipophilicity relationship is so it is linear or parabolic. So generally, as per our the partition coefficient or the solubility factor. Okay, partition coefficient factor with increase of the solubility or with increase of the partition coefficient, the biological activity will be increases. Okay, so in the very starting, the first factor, the first physicochemical parameter is the lipophilicity or partition coefficient or hydrophobicity here, or the solubility factor. So generally the this law it's log p value, right? So here the log p value is it is increased when it is increases, the biological activity is increases, means it is directly proportional actually, right? It is directly proportional. So generally when the log p value is right, log p value is greater than 0, right? When the log p value is greater than 0, then lipophilicity is more, and log p value is less than 0, the lipophilicity is less. Okay, means the polar compounds, okay, for non-polar compounds, log P value will be more. For non-polar compounds, log P value will be more. For polar compounds, log P value will be less here. Okay, so as per this statement here, where this lipophilicity, polarity and lipophilicity relationship is linear, right? Actually, the polarity and lipophilicity relationship is linear. But here they are not right, they are not specifically mentioned the relationship for this polarity and the lipophilicity, whether it is linear or the parabolic. So they are not specifically mentioned, right? So this is somewhat ambiguity here, right? So some ambiguity is there. So This is also one of the mistake or one of the wrong prediction of your hands here, or the disadvantage of these hands. So all these are the some wrong predictions of the hands analysis here, where they are not considered the metabolism factor, and they are not considered the conformational changes here at the receptor active site, and they are not considered the stereochemical factor also, and they are not right, specially mentioned the relationship between the polarity and the lipophilicity here, right? So all these are the disadvantages, are the mistakes done by your particular hands here. Okay, and besides all these factors, this particular hands analysis having some advantages also. And the advantages of hands analysis, you can see the use of descriptors, all the descriptors here, right? Use of descriptors like P, P nothing means here it is rho actually. So rho nothing but it is partition coefficient, and pi substituent constant. ES is a steric constant here, right? So use of descriptors from small organic molecules may be applied to biological systems here. Okay. So actually, this particular means considering all the parameters or the descriptors in one equation, it is applied only for the small molecules. It is not applied for the large molecules here. So even right, so we can apply this equation for the smaller molecules, right? And the predictions are quantitative and maybe evaluated statistically. Okay. So here the predictions, hence predictions generally these are quantitative here, right? These are quantitative means where they are having the values quantitative in the quantified. These are the values are the quantified means where the we can evaluate the values for all these descriptors here, right? So it provides some reliable evidences or the reliable confidence for this having the activity, biological activity, right? So this is also one of the advantages of this particular answer analysis. And quick and easy conclusions here. Okay, so generally you see here we are taking all the factors here. So then we will know that, okay, we'll know that. So considering which factor is increasing the biological activity, and considering which factor is factor nothing but you are the descriptor. Okay, physicochemical parameter is causing for the decrease in the value, which physicochemical parameter is causing for the increase in the value. So that thing will be known, right, easily here. And potential extrapolation substituents not included in the original analysis here, right? So extrapolation substituent means where the substituent actually here in this particular Hans analysis. Okay, so only few of the substituent values are predicted here, right? And some other value which substituents. We have various substituents here, right? So they are not predicted the values for all the substituents here. That extrapolation means the expansion. Okay, the expansion is not done. So that is also one of the right, some mistake of this particular Hans analysis here. And along with these advantages and disadvantages here, and some more disadvantages with Hans analysis is generally descriptors required for substituent being studied. So it is not right. So where you see the substituent descriptors required for substituents being studied. So and a large number of compounds required. Okay. So here generally this analysis, right? The analysis involves the trial and error method, the Hans analysis, or the actually this QSR method is right. So it is a trial and error method only. Okay, so we'll consider one group here, and we'll see whether it is increasing the reactivity or the decreasing the reactivity. If it is increasing, then we'll proceed with that one. If it is decreasing, then we'll reject that and we'll take some other group here. So that is, it depends on the trial and error method. So you need to check the large number of compounds, and predictions limited to structure class, and it is optimization technique and not a lead discovery technique. Okay, so here you see the generally where means we are optimizing the activity generally, right? The optimizing activity, and generally where it is not a discovering technique means actually we are not finalizing the structure by these predictions actually, right? Because just we are trying to finding the some reliable values here, right? And your QSR technique, it won't provide say 100%, right, correlation with your experimental values here, right? So no correlation, right, 100% correlation with your experimental values, but only the chances will be there. Okay, so when you right predict some values from this QSR, right? So there is a chance for achieving the, right. So there is chance for achieving the better values or the considered value in the experimental section here, right? So it is one of the easy approach, easy method, which is reducing the time taking and reducing the cost and all things here. Okay, and small molecular interactions are imperfect models for biological systems. So generally, you know that the small molecules not having much interacting points here. So it is right. Generally, the hands analysis, it is more applicable for the small molecules here. It won't applicable for the larger molecules here. Okay. So here the small molecules generally they are not having much interacting points like hydrogen bonding interactions or the ionic interactions, hydrophobic interactions. All these are not found in the small molecules because the size is small here. So they may not have the much okay the groups here. So it is somewhat difficult to check the reliability for this equation. So these are some disadvantages of this particular Hans analysis. So besides this disadvantage, it is having some advantages also, and it is one of the right approach, one of the approach uh, for the considering of the all these descriptors here to generate a PSR model. Then the Craig's plot. Yes. So this is also one of the multi-regression analysis, like your Craig's analysis. Sorry, like your Hans analysis. This is also one of the multi-regression analysis, but where this Craig's plot, right? So Craig's plot is taken in the right means it is two-dimensional. Okay, where the Hans analysis and some other some other factors are, it is involves only the right that experiments are only the one dimensional experiments here, but the Craig's plot involves the two-dimensional experiments here. Okay, so uh, what is two-dimensional here? Why it is two-dimensional, and what are the advantages and what is the use of this Craig's plot? We can see. Right. So actually, these are two-dimensional plots of one substituent parameter against another used in the rational drug design. And the plot is divided into four sections corresponding to the positive and the negative values of the parameters. So this is the one of the best predictions, one of the best advantage of with your Craig's plot here. Okay. So this Craig's plot, okay, so it provides the values for the negative phase right? The negative phase descriptors as well as the positive phase descriptors here, right? So then it is very easy to, right? Then it is very easy to generate the equation, and it is easy to check the relationship uh, for the biological activity with your descriptors here. Okay, because here if you consider always positive values here, then it is not right. So it is difficult to means correct that equation here. Sometimes if you take the negative values also, then the value means you get the okay, so better relationship here. Okay, so that's why this is one of the right attempt. Okay, the Craig is one of the good attempt to derive the uh, right equation, right? So actually, this Craig plot is, it is extension to the Hans analysis, right? It is extension to the Hans analysis, where means here also in the Craig plot also we take the, okay, we take the equation which is proposed by the Hans only, like for the multi-regression analysis. But here we are taking the negative phase values and the positive phase values here, right? So then we can adjust the values here. Okay. So by chance we can take the, for example, if you take the log p value, positive value here, right? And sometimes if you take the sigma value also positive, okay, then you can see the decrease in the right, decrease in the biological activity. So in that case, you can, for example, if negative values also available, then what you do, you take the positive C log p value and the negative sigma value. Then there may be the increase in the value biological activity log 1 by c value here. Okay. Or sometimes if you take the both values negative, then it is going to increase the value here. Okay. So it is one of the better method to uh, guess the value, means which value, negative value or the positive value is increasing the biological log 1 by c value here. Okay. So yes. So here, okay, get the high biological activity value 1 by c value. So you can pick up these the your required substituent. Okay, you can pick up the required substituent like sigma value and pi values here. Okay, so here you can see the various values in this Krieg's plot. Okay, here's a plus. Okay, actually, this plot is divided into 4 coordinates here, and the upper coordinates in the left side it is given plus sigma minus pi, and on right side plus sigma and plus pi. Right. So this is one of the important questions here in the examination. So this is repeated question. Craig's plot here. Okay, so on right side you see plus sigma and plus pi, and in the bottom face you see in the left side it is minus sigma and minus pi. Okay, in the above phase you see plus sigma minus pi here, and below it is minus sigma minus pi, and here is a minus sigma and plus pi. On right side you can see minus sigma plus pi here, and their values on this graph. Okay, you can see on. Okay, so you can see these are the values of various groups here, various substituents. Right. So in the range, for example, if you take the methoxy group, right, the methoxy group it falls in the negative phase. Okay, so here you can, for example, methoxy OCSC group here, right? So you can take minus 0.25 here, right? And here is a, for example, is methyl. Okay, so it is in the uh, right. So right side, you can take minus sigma plus pi here. Right. So based on this your requirement, so you can choose groups with their sigma and pi values here. Okay. And you can generate the equation. Yes. So this is Craig's plots as your hands analysis. This is also having some advantages and disadvantages here. So and it is having more advantages than your Craig's plot here. Sorry, hands analysis. And you can see what are the advantages of this Craig's plot. So here the plot shows clearly that there is no overall relationship between pi and sigma. The various substituents are scattered around all four coordinates of the plot. Okay, so the main advantage of this is, so generally this provides the positive values as well as the negative values here. Okay, so it is having the both. So it is providing both values here. So then it is um, right. So it is one of the good thing to incorporate in the equation here. And it is possible to tell a glance which substituent have the positive sigma, positive pi and sigma parameters, and which substituent have the negative pi and negative sigma parameters, and which substituent have one positive and one negative parameters. Right. So this is the advantage. So here it is providing the values for the positive and negative sigma and pi values here. Right. So based on your choice, based on your requirement of the activity, for example, you want to right, you want to increase the high biological activity, right? So you want to get the more potent compound with a high log 1 by c value. So then you can take which group is right, which group is giving that value based on the predicted values here, because the values are quantified here. So you can choose that right. So directly you can take the values here and you can substitute in the equation, and you will get the log 1 by c value, right? So because there is a little, means there is a standard values are provided here, so it is easy to right predict the it is easy to generate the equation here, right? So we have the positive values, negative values, one positive and one negative values, one negative and one positive. So all values are available here. So based on your requirements, based on your right, so you can choose both positive values or both negative values or one positive and one negative value here, right? So all this, yes. Then top list decision tree. So this is also one of the important question, and it is I think it is right. So the computers, if you have the computer knowledge or the mathematical knowledge, so it is the people which the people who are belongs to computers and mathematics, they will easily understand this top list decision tree here. Okay? Yes. So here the top list decision tree, nothing but it is a flow diagram. Okay, so it is a flow diagram as our solve the separation, right? So we have already we done in the experiment practicals for the separation of organic compounds. Okay, so where we are taking the binary mixture and we are added the ether, then one compound is soluble, another is not soluble yet. Then we are done the neutralization. So like this here also same thing here, right? It is a flow chart. The top list decision tree is a, so it is a flow chart where it directs or it guides the right, it directs a medicinal chemist to produce a series of analogs which should have greater activity than the lead compound. Okay, So this particular top list decision tree, so it guides the medicinal chemist or the chemist to get the more potent or the more active drug compound here than the lead compound. So what is lead compound basically? So lead compound nothing but the starting compound, right? The basic unit of your drug compound. We call this the starting material. Lead compound nothing but it is a starting material actually, right? So the starting material or the basic unit which is considered for the synthesis of the drug. Okay, for example, you are going to synthesizing a right paracetamol, for example, paracetamol. So para-aminophenol is a starting material. Okay, so we are doing the acetylation to the paracetamol, para-aminophenol. Then we are getting the paracetamol. So para-aminophenol is a lead compound here. That is a starting material. Okay, and if you are going to synthesize the aspirin, for example, then salicylic acid is a lead compound here, and we are doing the acetylation on this salicylic acid, and we are getting the acetyl salicylic acid. Right? That is a aspirin. Like that, here also the compound which is used to synthesis a drug compound is called the lead compound here. The starting unit we call the starting unit or the primary unit or the starting material. Okay, or synthon compound generally in the synthetic strategies we call this is the synthon actually. Okay, so here generally when we are going to invent or when we are going to synthesize a more efficient drug compound than the existing drug compound, right? So we'll take the existing drug compound as a lead compound and we'll do the some lead modifications. We do the lead modifications in order to get the more active or the more efficient drug, more potent drug compound than the existing one. Okay, so for this right for this analysis or for this means activity here, your top list decision tree provides or it guides us to synthesize a more potent drug compound here than your lead compound. And this top seal decision tree, okay, so it is a flow chart. You can see here, for example, here you see okay, so you take any compound. Okay, so you take any compound. For example, we are taking the benzene, right? So just you assume. So we are taking the benzene here. It is unsubstituted benzene. Okay, unsubstituted benzene we are taking. Okay, there is some compound is there, right? So we are taking some unsubstituted benzene here. Okay, so this is the unsubstituted benzene. Just we assuming this is the one of the drug compound here. Okay, benzene is a drug compound, and we are going to modify the benzene structure, okay, to get the more efficient or to get the more potent drug compound, more active drug compound here. Okay, so for that we are going to modify the structure of that lead. We are doing the lead modification. We call that is a lead modifications, right? So for that what we are doing, just here we are choosing one hydrogen here. So you, because it is symmetrical one, so you can take any one of the hydrogen here because all hydrogens are equal here. Okay, so you can take any hydrogens. Okay, so we are taking we are substituting the one hydrogen, right? Here is a hydrogen, for example, and this hydrogen is substituted with the, right, it is substituted with this particular chlorine. Okay, well, substituted with the chlorine, right? We are substituted this benzene hydrogen with the chlorine. Okay, it means like fourth position or somewhere here. Okay, right? Or you can say take it is a substitute, for example, right? So where, for example, it is substituted some R. Okay, it is a hydrogen. There is some group is there. Okay, then here the hydrogen, we are substituted this hydrogen with chlorine, 4-chloro, because here 4 is mentioned. So it telling that there is a substitution here, right? Substituent here. As per this flow chart, so just I am explaining. Or you can take unsubstituted benzene also. When you are going with your own example, so you can take unsubstituted or the substituted here. But here, just I am explaining this flow chart here. So here they are mentioned the 4-chloro means already it is substituted here, right? Some substitution is there, like just to assume, okay, here is some substitution here, some X, something is there, right? And now this fourth position with respect to of this one, right? So this is 1, 2, here is 1, here is 2, 3, and 4. Here is 5, here is 6 here. You know that there are 6 carbons on in the benzene where it is substituted, and this is a fourth position. And the fourth position, it is substituted with the chlorine. The fourth position, hydrogen is substituted with the chlorine here. Okay. So they are substituted with the chlorine. Means it becomes some substituted benzene with the chlorine here, like this. Some R or X, whatever you can take. Okay. Then when you replace the hydrogen with the chlorine, then the 3 things you will observe. Okay. The 3 things you will observe here. One is, okay, you will observe the 3 things here. So one is low activity, right? Another is, okay, yes, right? So you will low activity here. Another is equal activity. Another is a, right, medium activity, right? It is a, actually it is a medium. It is a equal, right? So low activity, equal activity, and the medium activity, right? So 3 points you will observe. Oh, sorry, low activity, more activity, and equal activity. These 3, right? L equal to low, M equal to more, right? E equal to equal. Means there is no change. Equal nothing but there is no change in the activity. Okay. So we observe this. Actually here this is M, not E. Okay. So this is L, this is M, this is E. Okay. So when you substitute the hydrogen at 4th position with chlorine, 4-chloro, okay, we observe the 3 things here. Low activity means less activity, more activity, and equal activity. These 3 points we got
Sir,
here. Yes.
so in our books it is given low L E M. M it is given on the last position.
Okay, then you make it M.
Okay, sir. Okay, sir.
Okay. So among these 3, 2E, you make one M. Okay, so I'm making this this M. Okay, you will make it. Here is a low. L is a low. E is a equal. This is a more. Okay, high. Right. So now you these 3 points we observed here. Now actually here we don't means we are not required the low activity. Okay, for example, when you substitute the chlorine at 4th position here, right? So if you observe low activity, so it is not required. Okay, and if you observe the equal activity, this is also not required here, right? So we are trying to increase the activity. And at what position, when you substitute the particular substituent at a different position, then which is going to increase and which is going to decrease. So that thing we are observing here. And here is a m, so we are getting the more. Okay, right. So now you reject. Okay, so we got, for example, it means here given three observations here, right? Here three observations. From the three observations, anything will be happens here. Okay, here is a possibility here given in this table where the given is three possibilities. Means substitution of the chlorine at 40 position, it may cause decrease in the activity, or there is no change in the activity, or increase in the activity here, right? For example, if you get the more activity or the increase in the activity, then you proceed with the chlorine. Okay, you proceed with the chlorine. If you observe the less activity or the no activity, equal means no activity, then you reject the chlorine. Don't substitute the chlorine here. Then you try with the different group. Okay, you reject the chlorine and you try with the different group, or you can substitute that chlorine at a different position. First we substituted it to fourth position, so now you try with the third position here, right? You try with the third position or the second position, means you try with the here is a para substitution. You okay, again you try with the meta substitution or the auto substitution. Okay, so like that, so that idea will be obtained from this top list decision tree. Okay, fine. So now yeah, so actually, so for example, if we got this like we observed for example, uh, we observe the more activity when we substituted the chlorine at para position, we observe the more activity. Okay, in that case what you do, you proceed with the chlorine, and you again you try with the more substitution of the chlorine. Okay, so now what you do, again then you proceed with the chlorine and you substitute one more chlorine. Okay, because the substitution of chlorine leads to increase in the biological activity. Then okay, then if you substitute one more chlorine on that, so there is a possibility for increase in the more activity here. In that case what you do, already the four we are substituted one chlorine into meta position here, para position here. Okay, there is some x something, there is chlorine, and it leads to the increase in the activity. Then we try one more chlorine at the third position here. Okay, dichloro some substitution here, right? 3,4 chloro dichloro, right? So we substituted one more chlorine here. Then what we observed here, again we get the three things. Again we'll get the three observations here. Either substitution of the dichlorine, right? There is a right chance for getting the decrease in the activity. There is a chance for no change in the activity, or you will get the more activity here. These three observations you will right observe, right? These three things you will observe, right? Because sometimes what happens here, substitution of one chlorine causing for the increase in the activity, and substitution of the second chlorine, right? So it may decrease the activity, or it may increase the activity. Anything will be happens here. Okay, so if it is means substitution of the dichloro, okay, two chlorines at 3 and 4 position, if it is decrease in the activity or equal there is no change in the activity, right? Then what you do, so you don't substitute the second chlorine at the third position. Okay, you substitute only one chlorine at para position, and you try with the different substituents like methoxyl group or fluorine or okay, and methyl or any nitro group or, so you go with different here. Okay, and for example, if you observe the increase of the activity when you substitute the second chlorine at third position here, right? Then Again, you try with the different substituent or the same substitution, same substituent here, right? You, for example, here, when we observe the substitution of the second chlorine to meta position, so we observe the increase in the more activity here. Okay, 3,4 dichloro, so it causes for the more activity M. Then you can try with the right, okay, trifluoromethyl. Okay, you try with the like this here. Here is some X here. So here fourth four chloro is substituted, and we observe the substitution of the chlorine increase the activity. Okay, substitution of second chlorine to third position also causing for the increase in the activity, right? Then we try with the different substitution instead of chlorine. Okay, so you can substitute trifluoro CF3, right? Instead of chlorine here, you substitute the trifluoromethyl to meta position and chlorine to para position here, right? Then if you observe the increase in the activity here, right? Then you replace up this chlorine with nitro again. Okay, so this is all these is a trial and error method only, right? This is by chance only. Okay, only just kind of puzzle where we are playing. Okay, so we'll keep one group and we'll see the we'll observe the means activity. Actually, it is the QSR, right? So it is some software will be there, right? So we'll check all these increase in the activity, decreasing in the activity. It will be obtained in the software here, right? So there are so many softwares are available for the QSR studies, like Sibyl software here. Okay, Glide here, Glide software, Sibyl. Okay, and Gold software here. Mercury. So Mercury, Gold, Sibyl, Glide, Studinger. So all these are the softwares here, right? So where the program is already designed, the program is designed for this purpose, right? So only thing is here you need to remove the one group and again you incorporate another group. Then you give the command proceed. Then the values will be appeared in the that screen here, and you see we are increasing in the activity or the decreasing here. Okay, again you remove that group, again you add some more group here, so like that. So that is everything will be right guide means everything will be obtained in the software here, right? So here the top list decision tree is guiding us which substituent you need to consider to get the better active compound, right? And for example here, this is when you get the more activity. When you substitute the chlorine at fourth position, if you get the more activity, then you go with this flow chart here. Okay. For example, if you get the less activity or the less or the low activity or the equal activity here, then what you do? Just you try with the another group. Okay, you go with the another group to fourth position. So you don't take the chlorine here. Simply you right substitute means you take the methyl group to fourth position because the chlorine is a electronegative group. So where it is causing for the low activity. In that case, you introduce the electron donating group here. This is the chlorine, the withdrawing group here, right? So withdrawing group is causing for the decrease in the activity. In that case, you try with the electron donating group like methoxyl group here. Okay, and you see whether the activity is increasing or decreasing here. Okay, then again the three phenomena will be observed like low activity, equal activity, and more activity here, right? For example, if you observe the upon substitution of the methoxyl group, if you observe the more activity here, then you try with the some other base like dimethyl, okay, dimethylamine, right? And again, you can go with the different groups, right? So here also same. If you observe the equal or the less or the equal here, then you just you reject that chlorine and you go with the different substituents like methyl or chlorine, means methoxyl or amines. Okay, so like that here. So here this particular topless decision tree, it's a flow chart. So it guides us to which substituent need to consider in order to increase the biological activity of a lead compound here. Okay. Next, cluster significance analysis. Right. So cluster significance analysis. The cluster analysis. So cluster analysis nothing but generally will take the more, right. So in this cluster analysis, actually we take more what is that, core structures here. Okay? So in the QSR model, to generate a QSR model, actually we'll take only one core structure and the different substrates, different analogs here, right? For example, if you take naphthalene here, right, and we'll generate or we'll construct the, right? For example, here naphthalene as a core structure, we are taken naphthalene as a core structure here. Here is the R something, right? And this is your core structure here. And by changing the R group here, we are generating we are building the various substituents here, right? So first you substitute methyl, then ethyl, you take fluorine and you chlorine are like cyclopropyl group here, so like that. So you means you construct the n number of analogs like up to 100 or 120 or whatever. So you have to generate the construct the various analogs and you check the right. So you go with the QSR right, QSR method here. QSR approach, right? So generally this is one core structure is considered for here. But in the cluster analysis, right, in the cluster analysis, so we'll take the variety of core structures. Variety of core structures means we'll take the naphthalene as, right, this is one core structure here, and some analogs for this naphthalene, and we'll take some pyridines, means examples here, right? Pyridine also one of the core structure. We will consider the, we'll construct some substituent for this one, and we'll take any heterocyclic or the any right. So 5-membered also, like, right. So like this. So yes, so means variety of different core structures are considered in the cluster analysis, right? So in the normal QSR analysis, we'll consider only one core structure, and we'll what is that? Means we'll take the different analogs here. But in the cluster analysis, we'll take the variety of different types of, okay, different types of core structures here, and we'll check the we'll generate the equations here. Okay, so that is a cluster analysis. So this is your QSR method. QSR studies qualitative structure activity relationship. So generally QSR, it is purely virtual, right? The virtual approach here, virtual studies here, means there is no experimental evidences are provided, and generally means by help of the computers or the software here. So we'll predict the values for this drug compound, and we'll get some values, and that values are reliable to the synthetic values actually, right? And the values, it may be correlated with the synthetic values or may not be correlated, and some 50-50 chances will be there, right? But the getting for the success rate here, the success rate in this QSR is, it is 50-50% here, right? So but only thing is, it is a very speedy process, and it is right. So no cost is required here, because only we are not using the physical, okay, physical chemicals here, like we are not using the solvents, we are not using any reagents, we are not using the reactants, anything we are not using here. It is completely, right, so dry lab, synthesis. It is completely dry lab synthesis. Means we are not using any wet chemicals here, right? So it is dry lab synthesis. And generally we call this is a in silico synthesis actually, right? So the CAD technology or the PSR, it is a, we call it is a in silico approach. In silico approach here, right? So we have three types like right. So in vivo, in vitro, right? In silico. So what is in vivo here generally? Where the synthesis is done, right? Then the method or the synthesis is done in the living organism. That is called the in vivo. Okay, in vivo analysis or the in vivo synthesis. And in vitro synthesis means here this is a biosynthesis. In vivo synthesis, nothing but it is biosynthesis here. It is biosynthesis. And in vitro synthesis, it is in vitro means test tube here. It is lab synthesis. It is lab synthesis, laboratory synthesis. So the synthesis takes place or the done outside the living organism or the biological system. And in silico, it is the synthesis or the method done in the some computer software here. These are the three approaches here, right? These are the three approaches which is useful and which is right taken up in the field of right chemistry science here. In vivo synthesis, in vitro synthesis, in silico synthesis. Okay. So this is the this is your QSR technique and like lead modifications, lead optimization. Okay. SAR studies. This is QSR studies, and one more method is there, SAR studies here. SAR studies nothing but structure activity relationship. Here is a QSR is qualitative structure activity relationship. And one more technique is a structure activity relationship. So we'll discuss about this structure activity relationship in the next class, right? So that SAR studies, it guides us to which substance we need to take, right? In order to increase the activity and the modifications, lead modifications. Okay, lead modification means, for example, you can change. For example, if the 6-member ring is there, right? So if you make that 6-member into 5-member, then there is a chance for increase in the activity, right? Or if you make it is 7-member, then there is a chance for increase in the activity. Or if any side chain is there, right? So if the side chain is with 7-member, right, chain here. So if you make it 3-member or the 4-member, then right 3 carbon, then it may be changing the activity. So that the means the impact of the different types of substrates or the rings size or the electronic means electronegative groups here. So all things will be guides us to for the means modification of the lead or the structure here in order to increase the biological activity, right? So the next class we discuss about the SAR studies. Okay, so I'm stopping here.